Hello, and welcome back to the course on Physics for Engineers. So we are now on the third lesson for Chapter 13, Magnetostatics. So before we proceed, let us first review some concepts. So we have found out in the previous lesson that the magnetic field actually curls around the current and vice versa. The current curls around the magnetic field. So by virtue of a right-hand rule. So if this is so in this figure, you will see that if the thumb, the direction is your thumb, the direction for the current is your thumb, then the direction of your fingers curling around your thumb is the magnetic field, and vice versa. So in the previous chapter on electrostatics, you have discussed about Gauss law, and you have defined the electric flux, where the electric flux uh, for a uh, material or a charge distribution uh, just depends on the charge enclosed by a Gaussian surface. So similarly, we will have a something like this in magnetostatics. Another alternative way to solve for the magnetic field. In the same manner as the Gauss law is an alternative way in solving for the electric field. So for this lesson, we will be talking about uh, Ampere's law. So Ampere's law is basically the analog of Gauss law in electrostatics. So in electrostatics, we have defined the concept of electric flux, basically how much electric field lines passes through a certain area. So in the same manner, we can define magnetic flux, a measure of magnetic field that basically flows, quote unquote, because they actually don't flow. They're basically uh, static in magnetostatics through a surface area. So how much magnetic field lines are flowing through or passing through a certain area A. So in the case of magnetostatics, since magnetic field are created by dipoles, there's no magnetic monopoles, then therefore the amount of field lines that goes out of the area also is the same amount of magnetic field lines that goes inside the area. Therefore, the magnetic flux for magnetic dipoles is always zero in magnetostatics. So the magnetic flux is always zero since it's always a dipole. So actually in electrostatics, the flux of a dipole, a pair of positive and negative electric charge, is also zero. So this is true for dipoles, even if it's electric or magnetic dipoles. It just so happened that there's no magnetic monopole. So we can actually use the magnetic flux to solve for the magnetic field and as an alternate way to solve for the magnetic field. So what we'll actually use is Ampere's law. So basically, this is the magnetism analog of Gauss law. So if Gauss law is an alternative of Coulomb's law, since Coulomb's law is for discrete charge distribution, and Gauss law is for continuous charge distribution, especially if your system or the charges are distributed with symmetry. So Ampere's law is also the same. But instead, we take the closed line integral of B dot dl, and this is equal to mu naught times the current enclosed. So dl here corresponds to our Amperian loop. So basically, if you have a current carrying conductor, you just enclose it with the line. You basically wrap it around with a line or a loop, and that is what we call our Amperian loop. The Amperian loop is the magnetostatic analog of the Gaussian surface. So I enclosed here is just the current enclosed by your Amperian loop. So in this case, the current enclosed by the Amperian loop is I. So the law of Biot-Savart uh, is the original way to solve for the magnetic field. The alternative way to solve for the magnetic field is Ampere's law. In the same manner as the Coulomb's law is the original way to solve for the electric field, and the Gauss law is the alternative way to solve for the electric field. So those are the symmetry between electricity and magnetism. So this is just the dot product, meaning this is just the magnitude of B, magnitude of DL, cosine theta, where theta is the angle between B and DL. So since this is a cross product, if theta is equal to 90 degrees, if the magnetic field and your DL is perpendicular, then this integral becomes 0. And this is maximum when theta is equal to 0. And minimum when theta is equal to 180 degrees because it becomes negative. So this is our DL here, the differential length or differential line length along the loop. You need to integrate along the closed loop. That's what this circle here means. So the circle here means you need to take the closed line integral. So again, it's similar to Gauss law, and similar to Gauss law, it's advantageous if your system has a symmetry. So if your system doesn't have a symmetry, then use the Biot-Savart law, the equation that we have presented in the previous video lecture. So let's have an example to show that we will get the same result as the Biot-Savart law. So let's try to find the field of a long current carrying wire. We actually know this one. The answer to this one is mu naught I over 2 pi r. But that is derived using the law of Biot-Savart. Now we will try to derive this using the concept of Amperes law. So we take the perpendicular distance r. At any point, a perpendicular distance r. This is the point where we want to find our magnetic field. And then basically, if you use Amperes law, you make a loop containing the point where you want to find the magnetic field. So this is our Amperian loop. It's basically a circle because this is a wire, and we're basically making a circle around our wire. So this is a circular loop. So we will make our magnetic field in the same direction as our DL. So that B that DL will just be B times DL. Cosine of 0 degrees, that's 1. So our B and our DL will have the same direction. They will actually curl around the current. So from this formula, cosine theta will just be equal to 1 since theta is equal to 0. B and DL have the same direction. And then what's left, and since the magnetic field at all points in our Amperian loop, since they are equidistant, we will assume that they have the same value. They're constant. So you can take the constant out of the integral, and you will just have the total integral of dl. The total integral of dl is basically just the total length of our loop here. And since this is a circle, then the total length of that is just 2 pi r, the circumference of a circle. So the I enclosed here, the current enclosed by our loop is I. So this is the current enclosed by our Amperian loop. It's I. So divide both sides by 2 pi r and we get this equation, which is basically the equation that we have been using to find the magnetic field a perpendicular distance r from a very long current carrying conductor. And originally, this equation is derived from the law of Biot-Savart. But we have derived this using the concept of Amperes law. So the Amperes law is again an alternative to the law of Biot-Savart. So another example, solenoid. So again, we already know the field of a solenoid. So what we will do is we will make an Amperian loop, and our Amperian loop here will be a square. So we will assume that the magnetic field outside is 0, and since our magnetic field here will have inside in this segment, we'll actually have 4 segments. This segment, this segment, this segment, and that segment. But these other segments will have 0 contribution. Only this DL1 will have a contribution. This DL2, DL3, and DL4 will have 0 contribution because there's no magnetic field here. Here, even though there's a magnetic field here inside, but the magnetic field and your DL is perpendicular. Basically, if they're perpendicular, B and DL is perpendicular, and cosine of 90 degrees is 0. So the integral of B dot DL for this side is 0. The same with here and the same with here. So there's only one contribution to this closed line integral here. Again, this is a closed line integral, meaning you need to integrate over all of the closed loop. But only one segment will actually contribute. Only this segment, the L1 segment, the L1. So only this segment will contribute. So that be that the L1. So the magnetic field here is uniform or constant, meaning you can take it out of the integral and you just have integral of dl1, which is the integral of dl1 is just the total length of this segment here. So the current enclosed is how much current is enclosed by your uh, uh, loop, Amperian loop. So in this case, you just need to count the number of turns, how many turns, and the amount of current, I. So it's basically N times I. That's how many currents are enclosed by our loop. So N times I. So DL here is basically just the length of your segment, line 1, this one. So mu naught Ni, divide both sides by L, and you will get the magnetic field of a solenoid with N turns and length L, which is exactly what we used in the previous lesson, where again we emphasized that this was originally derived using the law of B so far. But we have rederived this using the concept of Amperes law. So that one. So that is it for this lesson. Amperes law is to law of B and so far, in the same manner as Gauss' law is to Coulomb's law, an alternative to Coulomb's law. So Ampere's law is an alternative to the law of BU so far. Another way to calculate the magnetic field of a material, a current carrying material. So that's it for this lesson, and I will see you again in the next lessons for chapter 13.